everything that's happening so far? You do? Okay.
The homework that was due today, they didn't extend that?
There's homework due today?
Yes.
Cause there was,
You know, it was due on Sunday, and somebody talked,
no, there was one due on
No.
Sunday, and then there was one due today.
no, really?
Yeah, there's one, and it's been like that for like since last Thursday.
Sure, why not?
Very good.
And I tell you what, there's one that's due on the Monday of the week of the exam, right? I think. I'll extend that one too. The only concern I have is, you know, I don't want you, I want you getting ready for the exam, not cramming for the homework or something. But I'll extend it. But your job to remind me? Okay. Because if he doesn't do it, then it won't get done, right? It's all up to him. Okay.
I'll send an email today.
Huh?
I'll send an email.
Okay, good, good. Okay, what else? Anything else? Okay, I'm moving into chapter 17, and, which I think is the next homework, right? Is what's, what I'm extending is on 16, correct?
Yes.
Okay. All right, so, there's a couple of things that, I need to, make sure you understand. One is in chapter 17, it's like 12 was all about motion. Remember that? But it was points that were moving. Then we went into 13, which were free body diagrams. Okay? And then we came into 16, which was all about motion. And now we're into 17, it's going to be similar to 13, which is all about free body diagrams. So we're getting into free body diagrams. Now, when you do free body diagrams, you're using Newton's law. F equals ma, mass. And everybody knows what mass is, right? I'm not sure I do, but I know I got a lot of it. Okay? So, but you have a feeling for mass, correct? Well, now in chapter 17, things are going to be turning. And there is an inertia, a mass, that goes along with turning. And it's called moment of inertia. All right? Back in my day, it was a big deal when they would teach moment of inertia. Man, they'd beat you over the head with it. Boom, boom, because it was hard to calculate. Nowadays, it's easy to calculate. Why? Because normally what you do is you pick up a graphics package like NX or CATIA or whatever's your favorite one, and there's a button there. After you draw something, there's a button, you click on it, and boom, it'll calculate the moment of inertia for you. So things have changed, right? Now, I therefore don't want to spend a whole lot of time teaching you what you can do by clicking on a button. Make sense? However, just like if somebody were to ask you, what's 2 times 4, you're not going to go grab your calculator, are you? Better not, okay? So there's certain things you should know about moment of inertia that are just kind of common sense sort of things that people would expect you to know unless you're an idiot, right? So when you get your job and somebody says, you know, is that a big moment of inertia? And you go, huh? I don't want you to say, huh. All right, so right now, the next handful of minutes, I'm going to ask you some things and talk to you a little bit about moment of inertia. I'm not going to ask you to calculate moment of inertia. Okay, now you're going to turn your brains off. I know you are. Okay, don't do that. Okay, even though I won't ask you to calculate moment of inertia, you should have a feel for it. Got it? So stay awake. All right, let me ask you some things here. If I were to take a mass, let's see. Okay, if I were to take like a ring. Oh, come on, what the heck? Bless you. I don't know what I'm doing. Okay. If I were to take a ring of mass, let's say that's, you know, a piece of metal, and I bend it around. And I put some spokes in here, you know, just so it'll stand up. And put a hub on there, and I spin it. Okay? And this is a radius of, I don't know, 1 foot, 1 inch, 1 whatever. And it's 10 pounds, let's say. Can you imagine that? Okay. And then what I do is I take a ring, another 10-pound ring, and I do the same thing with it, but this time I have a radius of 2.
Does it have a hub?
Huh? It has a hub just like the other one. I'm not trying to fool you, but good point, right? So it's got a hub. I'm doing the same thing to it. All right? And here's what I want to know, and if you have your clickers, we'll see what you think. Number 1 is the left guy. Number 2 or A, B, whatever is the right-hand guy. And what I want to know is which one of these would be harder to speed up in spinning. You see what I'm saying? You know, they're sitting at rest, and you're going to come up there with your hand, and you're going to start turning them. Okay, which one would be harder to turn to get it started? Would it be the little guy here or the big guy over there? It's the same weight. It's the same weight. They're just at a different distance. Yeah, click in. Click in. Tell me what you think. Did it work?
Yeah, we're
Okay.
yeah,
Oh, yeah, yeah, well, it's a small screen, but anyway. Everybody weighed in? The left would be number 1, that one over there would be number 2, or A or B, you know.
Are you turning it from the edges?
Turn it from wherever you're going to turn it, you turn it the same way. So if you're going to be on the rim, or if you're going to be in the center. Okay, we're in the center, we're going to grab a hold of it right here, and we're going to go like this. Okay?
Oh.
You probably, I'm probably asking it wrong.
Yeah.
Okay? So this is, this is going to be mostly were you here? Okay, so let's see what y'all are saying. If I can figure it out. Okay. So 65% are saying B. I was hoping for a bigger percentage, right? Here's what's happening. The lighter, the shorter in this way that the mass is, the easier it is to turn. Okay, so if you got that one wrong, maybe I said it wrong, right? Maybe I've deceived you somehow. But if you're going, now, wait a minute, that doesn't make any sense. Come see me after class, because I want to make sure you got the right idea.
Which one is easier?
Well, you got a 10-pound ring. Here's the idea. You got a 10-pound ring, and it's this big around. And I'm going to sit here in the center. I'm going to start turning it, making it go faster, faster, faster. Okay? And then I have a 10-pound ring, but it's twice as big. Which one would be harder to speed up? The one that's twice as big. So if you got it wrong, okay, maybe I just said it wrong. Okay? But what I want you to have is a feel for the fact that in order to get these things to start spinning, the distance that the mass is out makes a big difference. Make sense? And you probably experienced it, right? The bigger the tire, the harder it is to get the thing moving. Okay? The other thing that will give you a large inertia. Inertia is it doesn't want to change, right? So it gives you a large moment of inertia is a large radius, which I've just asked you. The other thing is a large mass. So let's say you've got your arms out here, certain distance. If I pick up some weights out here and then I try to turn like this, it's harder for my body to turn because of the extra weight that's out there at my hands. That make sense? So you have a good maybe a feel for what moment of inertia is. Large moment of inertia means you got either big mass or you got mass at a large distance. One, or both, right? You get the idea? So if you want lower inertia to turning, you want to pull the masses in. Does that make sense? Okay. The other thing that you need to know about moment of inertia that people are going to expect you to kind of understand is something called the parallel axis theorem. If you have a body, any body, and it's going to have a center of mass. Are you familiar with what the center of mass is? It's a balance point. Okay. Do you know how to calculate the balance point? It's the centroid. Well, it's close to the centroid, but if you take the centroid and multiply by density, then you get the center of mass. For example, if this guy was over here, if this is an area, the centroid would be the center of the area. So if you cut it out of cardboard and then found the balance point of the cardboard, that'd be the centroid. If, on the other hand, this thing over here was all gold, and over here it was all aluminum, it would have a different balance point, wouldn't it? Okay, center of mass is different than centroid, but they're very similar calculations. Got it? Okay. So you know what the center of mass is. You could do it if you had to. I'm not going to put it on a quiz, but you could do it, yes? The way you really do it in the real world is you draw it up in NX and you click a button and it gives it to you. Okay? So I'm not going to beat you with it. But everything has a center of mass. Now, if you want the moment of inertia of something, say for example you have the moment of inertia about this point right here, about the center of mass, and you want the moment of inertia around some other point over here, okay, then the center of the moment of inertia around this other point is equal to the moment of inertia through the center of mass plus the mass times the distance squared between the two. Okay? Not on a quiz, but you better have that in your mind when you go to work, because somebody's going to say something and you're going to say something stupid and then you'll lose your job because they'll say, man, what an idiot this person is. Don't even know how to take 2 plus 2. Okay? It's called the parallel axis theorem. And usually they'll say, well, you can use the parallel axis theorem and shift it over. And you go, right? You need to say, yeah, I understand. I know what how do you do it? Well, what you're going to do is you're going to do it on NX. That's the way you're going to do it. Right? That's the way you'll actually do it. But you need to know about the parallel axis theorem. People will ask you about that or they'll say something about it, and you need to sound intelligent. Got it? You will use moments of inertia. Especially in Chapter 17, you'll use them on the test. I will tell you the formulas for them. Okay? Y'all had Calculus 2, I'm sure, or at least doing it now. And in Calculus 2, they are doing things like having you integrate to get the center of mass, and they're having you, or centroid, or whatever it is, and they're having you integrate to get the moments of inertia. Right? It's agonizing, isn't it? That stuff is, I mean, that's the stuff that I had to do. Man, we don't do that anymore. We just don't. Okay? So why are you taking Cal 2? I don't know. Okay. Here's another issue, and this is, I could care less if you use the solution manual. I really don't care. You're not supposed to, but I don't care. I'm not going to rat you out. I'm not going to come get you. I don't care. It's a learning tool. Use it. Here's the problem you're going to have. In Chapter 17, the author does problems different than what I do. I have done it his way. I've done it in classrooms when the professor made me do it, and I've done it in real life. I'm telling you, it does not work. Well, it works. It works. It's confusing for almost all problems. Very simple little problems that I would make up in a book that I publish. You can use the technique that the author's got. Okay? It doesn't work for everything. Well, it's confusing. See how confused I am already? Right? It's confusing to use that technique. What I'm going to do is I'm going to do like I've always done. I'm going to say there's one way to do it. Here's the one way you do it. It works every single time. You can do what you want. So when you're doing your homework, if you got a copy of the solution manual and you open it up and you say, man, this stuff doesn't look like anything Everett's doing, you're right, because I don't do it that way. Okay? If you want to do it that way on the test, that's fine. I'll grade it that way. But the odds are, and I've seen this historically, because I've taught this class for a long time, you're going to mess it up. You're going to try to use it. You're not going to listen to what I'm doing. You're going to do it your way, and you're going to make a mistake. And I'm going to hammer you, just like I'm going to hammer you if you make a mistake doing my way. It's up to you, okay? So I'm just warning you ahead of time that the solution manual is not going to do it my way. And I suggest you do it my way, but it's up to you. All right, so you know how to find center of mass. You have an intuition about moments of inertia, and I've warned you about the solution manual. How about we just do some problems? Is that good? Okay. All right, so basically the difference in this particular well, tell you what, let me just ask you, let's read this problem and you tell me what the difference is. What's the difference between 16 and 17, okay? So read this. The cart is given a constant acceleration of 6. Determine the force developed in the rod AC and the horizontal and vertical components at the pin B. The crate has a weight of 150 with a center of gravity at G, secured to the platform so it doesn't slide. Neglect the platform's weight. Okay, here's the picture. Why isn't this a Chapter 16 problem? It wants a force. right? Remember chapter 12 and the difference between 12 and 13? You count the degree of freedom. All right, so how many, by the way, how many degree of freedom is it? One, because the cart can go up the hill. Okay, stop the cart from going up the hill, nothing else changes. Okay, what does 1 degree of freedom mean? It means if you give me one double dot, I can find all double dots. Did they give me a double dot? Sure, they told me the A was 6. So I go, hot dog, man, I can get all double dots. That's not what they want. Right? So what do you do when you're faced with a situation like this? Because you're going to have to select between chapter 16 and 17 on the next test, right? Do I draw a free body? If you draw a free body for chapter 16, you're not getting any credit. It's not like I'm going to dock you, but you're wasting your time. It's not going to take you anywhere, and there's no credit there because you're doing the wrong thing, right? So you need to be able to select them. So this one, pretty obvious, okay? All right. So how do you do a chapter 13 problem? Free body diagram. Okay. So how many objects are there here? What are they? The crate and this body right here, right? Okay. So at most you're going to have 2 free body diagrams, at most, right? Let's see. Shall we do it?
Sure.
Okay. Which one do you want to take the free body of first? The crate, and I hear the crate, I hear the cart. Here's what I want to do. When you look at what they want the force at pin B, that's this guy right here, and they want the force in rod AC. See where that is right there? So here's what I'm going to do. I'm going to go in there and I'm going to take a body like this. Okay, everything inside this circle is going to be inside my system. And I'm cutting through pin B. I'm going to try that one. Why do you think I'm going to do that? Why did I cut it here at pin B? Because what I want is I want the forces at B to be between 2 things. They're always between 2 things. I want it to be between something that's inside and something that's outside. Otherwise, it won't come up in the free body. Make sense? Really? Right? Okay, why am I cutting this? Because you want that one as well, right? You want the force in this guy. Now, why do I not cut it at the pin? Why can I cut it here? For example, this would be dumb. See if I can get a different color. This would be dumb to come down here and cut like this. Why would that be dumb? First of all, it misses B. Tell me about the forces when you start cutting into a big piece of chunky metal right there. You know what they are? Man, you got shear forces. Yeah, it sounds like you've been in Chess's class. You got shear forces. You've got tensions. You've got moments. Man, you got a lot of stuff in there. Do you know what they are? Do you want to know what they are? Then don't cut it in the blue thing. You get the idea? Okay. So I'm gonna take around the black. Now, why is it that it's okay for me to cut the C right there? The AC. AC is special. Why is he special? You learned this in statics. He's a what? Well, so is B. There's only a tension or a compression, one or the other. How do you know? Well, it's a 2-force body, but you're right. It looks like a truss, right? It's a 2-force body. It's a take your pen like this and touch it in 2 places. Okay, now don't touch it in 2 places like this, because then you're not going to get the same feeling. But touch it in 2 places, one there and one here with your fingertips. What can you do to that? You can't do much. You can push it. Well, if I had glue on my fingers, I could pull it too, right? So you can only do this. What would happen if it was U-shaped and I could only touch it in 2 places? I could do this, right? All right. The forces that I can apply have to be right between my 2 fingers. See that? They have to go right between the 2 fingers. Now, sure, it's going to bend down here, but I'm not cutting a free body down there. I'm looking right up here. It's called a 2-force body. Okay, and it's either tension or compression. That's a 2-force body. That's why I can cut through here, because I know the force has got to go between that line, that point, and that point. Force has got to go right along that line. You okay with that? Okay. Draw the free body diagram. Just as a hint, this is a pin, so you're going to have 2. You could have 2 forces there. horizontal and vertical, or in two directions. So draw me a free body diagram there. Bless you. Is that close? There's some problems in there. Do I have a normal? Who's touching it? Where's the normal coming from? It's coming from this surface, right? Let's see, where's my highlighter? There we go. It's coming between this surface and the box, right? Okay, so it's between those two objects. Is the box in the free body? Is the surface in the free body? No normal. No normal. I know it freaks you out. No normal. Just like there's a couple of atoms in here, right? There's an atom right there, and there's an atom right there. Are they pulling on each other? You bet they are. How come I don't draw those forces in there? Inside, inside, man. Inside, inside. So no, there's no normal. I did make a mistake. At least one. It says it's 150 pounds. Is that weight or is that mass? Weight. So should I be taking 150 times G for the gravity? Oh, man. There we go. What about those B forces? You like those the way they are? Why not? Why do you want X and Y? Okay, I like that too, because what you're going to have to do, we're going to sum moments. You need to find the moment arm, the perpendicular distance. It's not impossible to find it, right? But do you want to do it? I sure as heck don't, right? So probably not smart, so let's change it, okay? And what would be convenient? Horizontal, vertical, that sounds good. Is that okay with you? All right. So here's what we'll do then. I'll get rid of those guys. Haven't quite figured out. Oh, man. Too much. Oh, golly. One of these days, man. There we go. Okay. I'm gonna put them in some other color, just because I don't want to try and erase them again. Okay, so here's a B. Whoops, pick it up. Oh man. Well, theoretically it works, huh? Okay. All right, so I'm going to draw a B1 here, BX we'll call it, and then a BY. Okay. Is that good? You like that one better? Okay. here's what we're going to do. We're going to sum forces, just like we did in chapter 13, and we're also now going to sum moments. So for every body that we draw, we're going to get 3 equations. Okay, now in 3 dimensions, because usually you're not going to do 2D. In 3 dimensions, you're going to get 6 equations. You're going to get x, y, z forces, and you're going to get x, y, z moments. Okay? But here we're going to do 3, because we're going to get an x and a y forces, and we're going to get 1 moment. Okay? So in the real world, the only difference is it's just twice as many equations is all. Okay? But don't panic, you get paid a lot more. Okay? So when we sum forces, you know how to do that, right? You're going to set it equal to mass, you know about that, times acceleration. Acceleration of what? When things are rotating, they may have different accelerations, correct? So what point do you pick? Any point you feel like? Center of mass. Newton said summation of forces equals mass times the acceleration of the center of mass. Sometimes it's easy to find the acceleration of center of mass, sometimes it's not easy to find it. Okay? And so the book has these handy dandy little shortcuts when it's difficult to find it. I'm just telling you, they're really hard. Okay? I would say, look, just go find the acceleration of center of mass and be done with it. Okay? So you write down summation of forces equals mass times acceleration. Now, in chapter 13, what did you have to ask yourself when you're getting to the point of summing forces? It's all the same as it was before. What did you have to ask before you did the summation of forces? And what coordinate system do you want to use? And what was the answer? What was the rule of thumb answer? The one that gives you the easiest acceleration. If it's tangent normal, do it. If it's, something, do it, right? Think about the acceleration before we get any further along. What is the acceleration of the center of mass? Any ideas? Is it 0? Looks to me like it's on a body. What's the angular velocity of that body? Okay, draw an angle on here. Okay, here's a line. Excuse me. There's a line. Draw a line somewhere else. Here's a line. They're making an angle, aren't they? Okay, as it moves, is that angle changing? Okay, now tell me what is the angular velocity of that body? 0. Okay, so any 2 points on this body, correct? Any 2 points, velocity of P equals the velocity of Q, any 2 points plus omega cross R. What's omega? 0. Any 2 points, do they have the same velocity? What about the acceleration? Any 2 points, do they have the same acceleration? Why? Because they have the same velocities. Why? It's not rotating, is it? It's not rotating. You see that? See it's not rotating? Okay. So they all have the same acceleration. Now you're telling me that G's got 0 acceleration? What is this acceleration here? Right there. Yeah, it's 6, isn't it? So how can G be 0? Now, tell me what the acceleration of G is. Nope. Why did you say 32.2? Because it's G, right? What did the physicists call that? Acceleration of gravity. And what did I tell you what they're doing to us? They're lying to us. That is not an G is not an acceleration of gravity. It is a force of gravity. And they're trying to confuse us so we don't get our jobs. Because they're jealous we make more money. Remember that? This case right here has weight. Believe me, it's got weight. Okay, I got weight too. All right, you see it setting there? Is it got gravity? It does? I don't see an acceleration. Is it accelerating? Then G can't be the acceleration of gravity. There's no acceleration of gravity. That's just the name of what they call it. Call it Peter if you want to. Peter, has it got Peter? Yeah, it's got Peter. What is it? It's a force. Right? G is the gravity is a force. It's not an acceleration. They're trying to confuse you. It's a force. Now, what's the acceleration of G? Don't tell me it's 32.2. That's the force. That's this thing right here. It's got to be 6. Because the body's not rotating, right? It's not rotating. So the body is moving together. If this point down here is going 6, how can this guy be doing something different? Right? In 1 second, he's going to be going faster. If he's not doing the same thing, they've just separated. Have you seen boxes do that? If you pull on them really, really hard, right? What's the acceleration? What is the acceleration of the center? Maybe that's what was confusing you. Oh, okay, all right. You see, I told you I don't speak well, right? What's the acceleration of point G? 6. Got to be 6. Why? Because it's not rotating. They've all got to be doing the same thing. Okay, now that you know you have an idea for the acceleration of the center of mass, tell me what coordinate system you'd like to sum forces in. Tangent normal? R theta? What do you want to sum them in? X and Y? Okay, let's sum them in X and Y. Do it. Did y'all get this for the X? Did I get it right? Shaking your head, you don't think so? I don't swear to it, but I think it's right. Yeah. Good question. It's EMA, right? A in what direction? In the X. Why X? Because I'm summing in the X, right? Summing forces in X equals mass times acceleration in X. So the acceleration is 6 up the incline, correct? So what's the X component? Right? Y'all see that? 6 cosine 30? Why is it positive 6 cosine 30, not negative 6? Yeah, because it's going up the incline, it's going to the right, accelerating to the right. By the way, did I assume that the AC is a tension or a compression? It's a compression, so I'm squeezing, I'm pushing. Is that right? So this guy down here, this piece right here, right there, is pushing the other guy. Is that correct? It looks to me like I drew it pulling. Am I not saying the guy down here that's not in the diagram is pulling the thing down? That's what that arrow, AC, it's got an arrow coming down. So the guy outside the body is pulling him down. Isn't that tension? When you pull on something, isn't that tension? Okay, let me ask you again. Am I assuming that AC is tension or compression? Tension. What do you think it is? Okay, so what do you think I'm going to get, plus or minus sign, when I solve for AC? Minus. I should expect a negative. If I don't, I'm going to go, huh? And I'm going to go back in and say, I bet I made a mistake. Because you all know it's compression, right? I mean, you just get a sense for it, don't you? Right? Can't always, right? But it's good, you know, an engineer should have a good sense for what's going to, oh man, that thing's going to buckle, you know, that thing's going to rip apart or whatever. That's important. Okay, can you do the y? Do the y. Sine of 30 here? Sine of 30 or cosine 30? I think it's because you got a 30 here that gets you to there, and then another 30 that gets you to the horizontal. So it's a total angle of 60.
Why don't you get the sign? It's you and cosine.
Oops. Cosine of 60 is the same as sine of 30. I never said I was a smart man. I sure am glad I'm not taking the test. Okay, let's see. Finish this one off.
Well, now you have to change the seat.
Oh, you smart else. Okay. Bless you. So this right here should be kind of a review. This is the same kind of thing we did back in chapter 13. So far okay? Now the next one is the only new one really, and that'll be summation of moments. Now, let's talk a little bit about where you can sum moments, because when you sum moments, you got to decide what point do you want to use. Okay? Now, what did they teach in statics? Exactly. Don't ever do that. Okay? The rule, right? And this is why they can get away with it. The rule that you must follow. And this is where I'm going to differ from the solution manual, because the solution manual will say, you don't really have to do that, but you have to add these correction terms. Well, I'm telling you, the correction if you're good, then yeah, it'll work. As long as you know what correction terms to put on there, you'll be good, right? I can never remember those things. Plus, they're really confusing when you do real problems. They're not so bad on textbook, but real problems, ooh. So I avoid it, okay? So if you want to avoid all of that, then here are the rules. You can sum forces around 3 places. Ready? Yeah. Get your notes, because this is not quite gospel. Number 1, you can always sum moments around a point that has no acceleration. So tell me about what they told you in statics. In statics, did they ever have points with accelerations? Okay, so then they could sum anywhere they felt like. Right? So they weren't lying to you. It's just that they never faced a problem with acceleration. You cannot sum moments around any points that have an acceleration. You just can't do it. Why? You'd have to add correction terms. If you want the correction terms, read the book. I'm not going to teach them to you. Okay? But they're there. They're just confusing. Okay, so sum them around points with 0 velocity. Number 2, sum them around the center of mass, no matter what it's doing. You'll be okay. Around the center of mass, yeah. Zero acceleration, what did I say? Okay, well, it's acceleration. Has to have 0 acceleration. It could be moving at a constant speed. You can sum moments around. Has to have 0 acceleration. So that's 1. That's 2 is the center of mass. You can always do it around the center of mass. You may not want to, but you can always do it there. The third one is a really weird one. And you'll rarely ever find it. Okay, rarely ever find it. It's used when people are deriving, fancy equations. But it's if you have a point that happens to have an acceleration, that happens to pass through, the line of action pass through the center of mass, you can sum there. You might as well cross that one off, man. They exist, but you'll never find it. I mean, it's hard to find them, because most of the time you have no idea what the acceleration is doing. So you might as well just forget about that one. But it does exist, right? So just so I'm not lying to you. So where are you going to sum moments? 1 or 2 places. That's what I recommend. 1 or 2 places. Center of mass or a point that has no acceleration. Okay. You see any points in here on the crate that has no acceleration? Are you sure? I thought we all agreed that there was no omega. That means all the points have all exactly the same accelerations. Otherwise, the thing's breaking apart, isn't it? Okay. Well, then, if point B has got an acceleration of 6, they all got 6, don't they? So, can you find a point in the body somewhere that has 0? No, they're all 6. Right? Okay, so where are you going to sum? Center of mass. Sum it around center of mass. You remember how to sum moments? Okay, it's R cross F, right? Which, or it's the moment times the perpendicular distance. Okay, so let me show you how I would do it up here. Okay. Whoops, come on. Okay, here's what I do. I'm gonna find the moment of bx. Okay, so what I do is I come in here and I draw a line along bx. For some reason, there we go. I draw a line along bx. Then I find the center of mass. Here it is, right there. Right there. And I want the distance between that x and that line I just drew. What's the distance? Yeah, is it this distance here? That distance right there, right? That's the perpendicular distance from the force. A lot of times what I see students doing is they say, oh, there's the force, and they'll find the distance from there to there. See that? That's not right. Is that perpendicular? No, it is not. So what you do is you just extend the line for as long as you need it to be. And then I think it becomes pretty clear that you want perpendicular distance. So that distance is 1, I think it is, in the diagram. Okay, so what's the moment of bx? It's what? I think it's bx times 1. Is it clockwise or counterclockwise? Counterclockwise? Okay, now, counterclockwise. Why are we going to choose it as positive? You're right. The right-hand rule. I is that way. That's because that's what I always do. J is up. Right-hand rule. Positive rotation is out. So we're going to say that it's that's a counterclockwise. That's the moment, counterclockwise. Can you all see the direction? Or should I talk about that? Right? Think of it as being pinned down. Hold it down gently with your fingers at G. And if you pulled on BX, which way would it turn? It would turn that way, wouldn't it? Okay, so it's counterclockwise. So that's going to be a plus. Right? Okay, get the BY. What's the perpendicular distance for BY? It's not the same. Okay, so it would be BY times 2. What's the direction, plus or minus? Okay, how about that AC? What are we going to do with it? Right. What I would do is I'd break it down into 2 pieces, into a vertical and a horizontal, and then do that one. If you're really good at geometry, you can draw a line from here and see if you can find the perpendicular distance. I'm not good at geometry, so I'm going to break it down into 2 pieces. Okay? So the vertical piece is AC cosine 60, right? Yeah? AC cosine 60? Oh, I'm sorry, that's a horizontal. Did it again, didn't I? Okay, so AC cosine of 60. That's the vertical piece. Okay, so let's find the moment arm. What's the moment arm of that vertical piece? Right, so here's the force right there. Yeah, looks like 1 to me. And is it positive or negative? Positive? Okay, I agree. Dadgummit. Okay. It's Monday, right? Okay. The moment arm is still 1. What direction is it? We're doing AC. We're doing the horizontal, right? Am I? According to my diagram, which way is the horizontal AC?
Well, you have your diagram the wrong way, like you said.
I do.
Well, you wanted it for compression.
No, this is tension. I drew it in tension.
Yeah, you wanted it for compression.
Isn't it that way?
Yes.
Okay, if it's that way, hold it down gently there and pull here. Which way does it go? Clockwise. What's that? Negative. It's a negative direction. Yeah or no? Argue with me. I'm not saying I'm always right. Apparently today I'm always wrong.
On mine, I just switched to.
Yeah, well, because you have yours in compression, so you're going to have just the opposite of what I have. And then your number will be opposite mine. So if I get a negative, you'll get a positive. Because it is in compression, right? All right. So the moment arm is still 1, but I screwed up on this guy. This is this should be a negative. Okay, now the vertical, right? Now we'll get the vertical. That'll be an AC sine of 60. And the moment arm there is 1. In what direction? Anybody else creating moments? I got the BX, I got the BY, I got the AC. What about that 150? Ah, good. Okay, so what is this equal to? Well, according to Newton, brilliant man that he was, according to Newton, this is equal to the moment of inertia of what? Of the crate, of the thing in the free body. Whatever you chose in the free body, if you put 2 masses in the free body, it's the I of both of them. If you have 1 mass in the free body, it's the I, the moment of inertia of that body. Got it? Whatever's in the free body. I. Around what point? The same point you're summing moments around. So if you sum moments around B, the wrong thing to do, but if you did, it would be I around B. Where did we sum them? Center of mass. So this would be moment of inertia. It's usually called I around the center of mass, which was point G. How do I find that? I will give you formulas for that on the test. How would you find it in the real world? You would draw the thing in X and you would ask for the moment of inertia. Right? Or you'd get a dynamics book and you'd read the chapter on it. Okay? Whatever you want to do. Times the angular acceleration of the body. So it's like MA, it's I. That's your mass. And your alpha is your acceleration. So it's I times alpha. Why did I put it in as a positive alpha? What am I assuming about alpha? Which way is positive? I'm assuming it's accelerating counterclockwise. Do you know what the alpha is? Wait a minute. It's 1 degree of freedom. Right? It's 1 degree of freedom. Didn't they tell me 1 double dot term? Can't you find all double dot terms? Can't you find alpha? Think about it. What is alpha? Why 0? Angular velocity is 0. Is it always 0?
No.
It's not? Okay. When does that angle, right?
Oh, in that
Well,
case,
in this case, no.
Okay. In this problem, there is no omega. There will never be an omega unless something breaks. Nobody has an omega ever. So there's no change in omega, right? So what is the alpha? 0. So this guy here is 0. Now, how many unknowns do you have? Bx, by, ac. How many equations you got? Problem solved. Right? Can you solve 3 equations for 3 unknowns? Yes, you can. Do you want me to spend time doing it? No, you don't. Okay, let's go to the next one. But you can do it, right? Are you saying no? Okay. How did that one get in there? Oh, it's the second one. Yeah, I remember now. That's what happens when you prepare things. It's like, what? Okay. Let's see if this one's any different. The strut AC can withstand a maximum compression of 150 before it fails. Determine the cart's maximum permissible acceleration. The crate has a weight of 150, center of gravity G, blah, blah, blah. Okay, what's different about this one? How do you know it's a chapter 17? It's 1 degree of freedom, and they're asking you for an acceleration. Isn't that chapter 16? Okay, what's the degree of freedom? 1. All right, that means if you give me a double dot, I can find all double dots. Did they give me a double dot? That's why it's a 17. See that? That's why it's a 17. I could have done the same thing with this problem over here. Let me change this problem over here. Here's what I'll do on a test. If the cart is given a constant acceleration of 6, blah blah blah, and the force in the rod can withstand 500 pounds, what's the acceleration of G? Right? If the cart is given a constant acceleration of 6 up the ramp, and AC can withstand 500 pounds, what's the acceleration of G? Do you need a free body for that? Unless you're worried that, well, maybe the thing's going to bend and break or something, fall apart. Then you draw a free body diagram because you want to know what's the force in AC to make sure it's less than 500, right? But see, I can change the words just very slightly, and I think I can fool you into doing the wrong thing. Don't let me fool you. Got it? And you say, oh, you're just mean. No, I'm not mean. I'm trying to get you ready to be an engineer. Okay. So why is this one, if I were to say, if the strut AC can withstand blah, 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 and A is given an acceleration of 6, what's the acceleration of G? Do you need a free body diagram to do that? See what I'm saying? If the acceleration of B equals 6 up incline, what is acceleration of G? Unless you're worried about the strut breaking, the answer is 6. You see that? Okay. Can you? I hope you can begin to tease out. This is a 16. This is a 17. This is free body. This is no free body. Yes or no? No? Okay. Come see me in the office. You with me? You're staring at me like I'm an idiot, and I know I'm an idiot, but don't stare at me. Okay. Is this problem really much different than this one? You're going to do a free body. What's the free body of? Of the box, right? Of the box. You're going to sum forces. You're going to sum moments. What's different here as before? Yeah, in this particular case, let's see if I get my highlighter. Here's my highlighter. Over here, we knew this was 6. Now it's A. Right? Over here, we were solving for AC. What is it now? 150 or whatever it was. Right? The load that it could handle. And you know it's compression. They said it was compression, right? So for this guy, this would be plus 150 or whatever the number was. Is the problem any different? Do you really want to do it? No. It's the same thing. The equations are going to be the same thing. You got it? The procedure's the same thing. It's just different unknown. Okay. How about this one? Trailer with its load has a mass of 150 kilograms and a center of gravity, blah, blah, blah. It is if it is subjected to a horizontal force of P, oh, by the way, I say center of gravity a lot, and the book says center of mass. They're not exactly the same. The only way they would be different is if the G changes. How would that happen? If you're building a huge structure, something like the space station, for example, it's pretty big, and you're flying it so that part of it is in one G and the other one, or the G down here is different than the G up here, the center of mass won't be the same. It's the center of gravity, okay? But, I mean, okay, maybe you'll be a rocket scientist. I don't know, okay? But that's the only reason the center of gravity is different than the center of mass, okay? But it's the center of mass, I get sloppy. It's the center of mass that you need, not the center of gravity. Just like the centroid is different than, or the, centroid is different than center of mass if that has a different property, like half aluminum and half steel. Then the center of mass will be different than the centroid. Okay. Trailer with a mass of blah, 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 centers G, horizontal force at P, determine the trailer's acceleration, normal force on the pair of wheels at A and B. Okay, how do you do this? Degree of freedom, very good. It's always the same. I'm really, you should be getting bored. You should be yawning. Okay, what's the degree of freedom? 1, okay. What does that mean? It means if you give me a double dot, I can get all double dots. If you give me a dot, I can get all dots, blah, 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 blah. Okay. What did you give me? Did you give me a double dot? Darn it. Okay, because otherwise, if I said, I'm pulling on it with a force of P, it has an acceleration of 6. What's the acceleration of the upper left corner of that box? Well, 6. See how trivial that is? No free body or anything. Okay, so do you need a free body? Yeah, you need a free body, right? Because what are you trying to find? You're trying to find the acceleration, but I didn't give you a double dot. I did not give you a double dot. You see that? Right. Okay, so you need a free body. What are you going to draw the free body of? I see 1, 2, 3 things. I see those 2, a safe, a filing cabinet, and a, what are you going to do? Just the cart? You're going to take off those, you're going to take off the filing cabinet, etc.? Why? Huh? Well, it says the trailer with its load has a mass of 150. So first of all, I don't know what the masses are of those 2 little pieces. Plus the fact that you pull them off, now all of a sudden you have those normal forces, you got friction, you got all that, right? Do you really want to deal with those? Do you or not? No? Okay, then I don't think I'd take them apart. Now, if somebody were to say, how much force is on the trailer between the bed of the trailer, because it's made out of cardboard, I'm afraid it's going to sink in. Okay, well then I need to know the normal force. I take them apart and find out what the normal force was, right? I don't care. I assume the trailer's not going to fall apart. Okay? So what are you going to take the free body of? All of them? Okay, let's do all of them. You draw the free body diagram. Oh, which way you want? Oh, I'm sorry. Did I do it right? Hope so. I hope I'm doing something right. How come you have an A and a B? How come I have an A and a B? Exactly. Why do they go in there? Because what is in the free body is the wheels and the cart and right, all that stuff. Nothing else. And so the A is coming between the normal force between the tire and the floor. Floor's outside, the tire's inside. B is the same reason. Okay, 600. Somebody's got their hand on there pulling it. They have to. They didn't show it to me, but the forces just don't magically appear. They've got to be between something. Okay. Now what? Some forces. In what direction? Tangent normal? R theta? X and Y? How come? What made you make that decision?
Because all the measurements are
No, that's not why. Because the acceleration, right? Forget the measurements. You can get measurements. Those are easy. What's hard in real life, what's hard is finding the accelerations. That's what's hard. So you should practice saying, well, you know, where's the acceleration? Well, what is the acceleration? What's it going to do? Of what point? The center of mass. Okay, so think about the center of mass. What is the center of mass doing? Horizontally? Okay, so that looks to me like that's an ideal I and J sort of thing. Okay, so we're going to sum forces in I and J. Okay. And thank goodness the dimensions work out too. You know, but that's not why I made the decision. Okay, sum forces in the X. Did y'all get that one? How about Y? Did you get that? Why is it 0? Because it's going horizontally. So write the position. Position is equal to a constant plus x. Right? Take a derivative. Derivative of a constant, 0. So everything in the vertical is going 0. It's very common for students in dynamics to say, you know, something's got to be 0, and you start throwing zeros in for accelerations. Don't do that. It is rare that you'll have a, I mean, it happens, but make sure you know why you're putting a 0 in there. Don't just arbitrarily throw one in. Okay? And then a lot of times you think, oh, well, the normal forces are always equal to 0. No, they're not. Okay? If you like, I'll give you an example. Okay, now what are you going to do? Moments. Okay, around, how about, you know, it'd be nice if I did them around A. What do you think? Why? Because I said not to, right? You can read the book, and the book will show you, oh, yeah, you can put in these correction terms. You're on your own. If you want to do it, you're on your own. Okay, I'm going to sum them around the center of mass. Why? Because I can't find a point that has 0 acceleration, so center of mass is always a good choice. So I'm going to sum moments around G. All right, so I'm going to get 600. And which way is positive? Counterclockwise. I is that way, J is up. Right-hand rule, counterclockwise is going to be positive. Okay, so here we go. I've got a 600. What's the moment arm? 0.75, I think you're right. And positive or negative? Everybody agree it's positive? Imagine that you're holding it gently at G and you pull on it with the P. You're going to turn it this way. You're going to turn it like that. That's positive. Okay, how about A? I have an A. What's its moment arm? Looks like 1.25. Positive or negative? Positive. How about B? B, moment arm of 0.75. Negative. That equals moment of inertia. Around what point? Times alpha. Which way do I assume the alpha is going? Positive, because I put it in as plus alpha, I alpha, so I'm assuming it's positive. It's counterclockwise. If I solve for alpha and I get a positive number, I'm right. Get a negative number, I'm wrong. What is alpha in this case? How do you know it's 0? Yeah, because there is no angular velocity. How do you know? Because paint a line right here. There's a line on the cart. Here's a one on the floor. Do those angles ever change? Okay, so it has 0 angular velocity. Does it always never? No, never. Okay, then it has 0 alpha. So this guy here is 0. The next section, they're not 0. Okay, so how many unknowns do you have? AX, capital A, capital B. How many equations you got? 3. Can you solve it? Do you want me to do it? No.
Could you just explain when you got the length of 0.75 to 600?
Yeah, it's this distance right there minus this one,
Oh, okay, gotcha.
which somebody told me it was 0.75, and I believed them. Okay? See how boring and dull these are? Yeah. Summing moments? Yeah. Then what you're going to do is you look back at the free body diagram. You're going to take the perpendicular distance from each of the forces. So, for example, the way I do it, because I get confused all the time, I get a different color, and I do this. I say, okay, here's the force A. I'm looking at A, so I draw a line right along A. Now you want the perpendicular distance. You want that distance right there. That's what you're asking me, right? Okay, and then for B, I say, okay, I'm going to draw a line along B. And then I'm going to find the perpendicular distance. It's always been that way. If you say, that's not what they taught me, yeah, they did. But it's always like that. And then how about the 600? Okay, I'm going to draw a line along the 600. And then I'm going to find the perpendicular distance. Okay? And R cross F works if it's like in 3D and you got weird positions. It's easier to take the R from, 3 feet this way, 2 feet that way, and 6 feet up, and then cross it with the F. But for textbook problems, perpendicular distance is usually the easiest. Okay, any questions? Any other questions? Not quite sure how we're doing on time. Oh, okay. Let me slip in something, if you don't mind. This will get you ready, I think. Well, I think it's important. Okay, here we go. What if I had something like this? Let's say I had a rod. And I pin it down right here. So basically it's going to go like this and whew, fall. Okay? And I'll tell you that I'll tell you the mass. I'll tell you the length. I'll tell you the center of mass is right here smack in the center. I'll tell you all of those things, right? How big it is and everything else. All the things you want to know. Here's what I'd like to do. I'm going to release it from rest. I'm going to hold it out there and then I'm going to let it go. I'm holding it with my hand, then I'm going to let go, and it's going to fall. What is the angular acceleration right when I let go? Okay, good guess. Anybody else want to guess, or you want to figure it out? I warned you, right? Be careful, because you're going to say, oh, this has got to be 0. Okay, well, if alpha were 0, it has no acceleration. If it has no acceleration, acceleration is the change, angular acceleration. Angular acceleration is the change in angular velocity, correct? So you're telling me it has no change in angular velocity, correct? So what's its angular velocity when I let go? Nothing. It doesn't change. Have you ever seen them go like that? Magicians do that, right? Ooh, come on. They're fooling you. Is it stay like that? No. Can the angular acceleration be 0? No. Be careful, I warned you, right? You're going to say, oh, it's got to be. Well, no, it isn't. How are you going to figure it out? Is this a chapter 16 or chapter 17? Right? I mean, you're staring at me like I'm speaking Greek, right? It's not Greek. It may not be English, but it ain't Greek. I know that. Right? So you say, well, let's figure it out. Okay, is it chapter 16, 17? How do you know? Is that where we started? Where do you start all dynamics problems? Count the degree of freedom. What's the degree of freedom? 1. What does that mean? It means if I tell you a double dot, you can find all double dots. Did I tell you a double dot? No. What are you going to do? not chapter 16, right? You want a double dot. That's what you want. You want a double dot. Did I give you one? You thought I did. Gravity is not a double dot, right? It's a force. Right? It's a force. It's not a double dot. So, what are you going to do? Free body diagram. Let's do a free body diagram of this. You see how they all start? And you know, at least half of you are going, I haven't a clue what you're talking about. Count the degree of freedom. If you don't know what to do, I faced it, right? People come in and they'll, you know, people with money, right? You don't want to look stupid in front of people with money because they may give you some. And right? And they'll come in and they'll ask me something. I haven't a clue. I don't know what this person's talking about. So what do you think I do? I count the degree of freedom. I start thinking about it the same way I've always thought about all problems until all of a sudden it kind of snaps in there. Oh, okay. The answer's 43. And then I look really brilliant, right? And they give me some money. You know? Okay, so you're confused. You say, man, I haven't a clue what you're talking about. Okay, count the degree of freedom. Is it chapter 16, 17? Do I need a free body diagram? Yes, you do. Draw it. Okay, here we go. I'm going to kind of simplify it a little bit. There's the body. What kind of forces do you have back here at the pin? It's a pin, right? Could be vertical and horizontal for all I know. Huh? And a moment? Well, it's a hinge, right? So can it hold me up? No, so it's going to fall, right? So is there a moment back there? Okay. So I have a, let's call that point A. So I could have an AX, or an AY, excuse me. Which way am I thinking it goes? Up? Okay, I have no idea what it does. Here's an AX. If I solve for them and I get positives, then I'm right. If I get negatives, I'm wrong. Where other forces? You got any other forces on there? Center of gravity, and what do you got there? Wait, mg. Right? It's not an acceleration of gravity that it has. It has a force of gravity. That's what it's got. Right? Okay. Anything else? What are you going to do? Some forces? Okay. In what directions? Is it going to be X and Y? That's fine. We'll do X and Y. And why are you saying X and Y? Because the forces are all X and Y?
Oh, no, we're not doing
What are you going to use? How are you going to find the acceleration? Let's think about that. Are you going to use a loop? You're going to use tangent normal? You're going to use special points? You're going to use special points? You're going to use special points? I'm going to use special points. Now, if you say no, I'm going to use tangent normal. If you can visualize it and say, man, I'm going to use tangent normal. Okay, well that's fine. I won't get mad at you. You say, look, that's fine. But you got to think it through and say, what is it you're going to do for the acceleration? I'm going to use special points. That always ends up in I's and J's, right? Because I'm going to cross products and all that kind of mess. So I'm going to pick I and J. That's why, not because the forces are lined up, but because of the accelerations. Okay, so let's sum forces in the horizontal. AX equals mass times the acceleration of point G. This is point G in the X. Right? Sum forces vertically. AY equals, oops, minus mg. Oops. mg equals mass times acceleration of g vertically. Now, which way did I assume AGX was? To the right. I really don't know what it's going to do, but all right, I'll get a plus or a minus and then I know. What did I assume about AGY? What did I think it did? Did I? What did I plug in? Did I put in a minus MA? Okay, then what am I saying? Oh, I think it's going what? Up? Now, is it going up? Okay, so if I get a positive here, what do you think I'm going to do? I'm going to say, ooh, I made a mistake. Right? Because anybody knows it ain't going up. Or is it? Right? You get the, because you could be doing a really complicated problem. You say, I know it's going to the right, and all of a sudden it goes, no, it's going left. And you go, huh? What? And then, oh, that's right. Yeah, this is, okay. So it doesn't mean that you made a mistake. It just means either your logic's not right or whatever. But yeah, in this case, it's so simple. If I get a positive number on that, I'm going to go back and look for the mistake I made. Okay. All right, now what? What do we do? I've done 2 already. Moments. About where? G? Is that really where you want to do it? Why? Can you do it around A? That's the first question. What does it have to have? No acceleration. Does this, what kind of, it's a special point, right? Isn't it in permanent contact with the ground? Then tell me about the acceleration. Same as the ground. Does the ground have acceleration? No? Okay. Then can I sum around A? Is that smart? Yeah, because like in statics, man, you got 2 of them, they disappear. Okay, let's do it around do it around A. Okay, so I have mg. Let's say this is a length L. So G is right smack in the middle. It's a nice uniform rod. MGL. Y'all agree? Positive or negative moment? It's going clockwise, correct? Right? I is that way, J is that way. Positive is counterclockwise. So it's going to be a negative. Anybody else have moments? Okay, and this equals 0, right? No, this is equal to moment of inertia around what point? A. Times what? Alpha. Which way am I assuming alpha goes? Counterclockwise, right? Because I plugged it in as a plus I alpha. So I'm assuming, now, which way is it really going to go? Clockwise? Okay, then I'm expecting to get a negative number when I solve for alpha. I don't panic. I just say, that's what I'm expecting to see, that I'm going to get a negative. Okay? How many unknowns? Really? Do you know that? Do you know this? Come on. Shut up. Shut up. I don't know why it does that. Did I tell you my wife dropped her phone, right? So she takes my phone. And so I'm without a phone. So my son comes in and says, well, I got this old phone. I said, okay, great. Right? And I said, great. And then this, and so I say, well, and he says, yeah, it always acted up on me too. I'm thinking, okay. From your son, you wouldn't expect that, would you? Okay. Here's another. Do you know AGY? Okay. Do you know alpha? How many unknowns? 5. How many equations? Oh my gosh. Here's a problem that cannot be solved. You believe that? Okay, then what is wrong? Something's got to be 0. Let's throw some zeros in. Let's throw 2 zeros in there, right? Which 2 do you want to pick? Is that the right thing to do? That's not the right thing to do. That's what you'll do on the panda, right? That's not the thing to do. What are you missing here? How many degree of freedom was it? How many double dot terms should you have? 1. How many do you have? How many? I see AGX, I see AGY, I see alpha. How many should you have? 1. Isn't it possible that if I find 1, I can get the other 2? It's exactly what it is. Okay? So there is an equation that will tell me what those 2 accelerations are in terms of the third one. So in other words, I'm going to write AGX equals, blah, 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 AGY equals, blah, 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 and it'll have alpha in it. See where I'm headed with this? How do you get those equations? From the loop? From the rope? Special points. How many special points you got? What are they? G and A. How many equations you going to write? 1. It's going to look like AG equals AA plus alpha cross R minus omega squared R. Got it? Okay, that's where we're headed. I'll post that. Okay? All right. Oh, I have I have the exams in my office if you want to come get yours.